Hello, I'm Stephen Bryant, and on behalf of my colleagues at the University of Calgary, appreciate the opportunity to present a keynote in this session. We wanted to tell you about something we're calling carbon negative crude oil and how it can contribute to any and all pathways to net zero. So the key points here are that carbon negative crude oil is something, it's an option for carbon dioxide removal that can be implemented rapidly and scalably. Field data support the fact that we can actually produce carbon negative crude oil. And if you can incorporate carbon negative crude oil into your pathways, you can deliver more services, broadly speaking, within any given carbon budget. Okay, at this point, you're probably saying carbon negative and crude oil, that's a contradiction in terms. What are we talking about here? So let's tell you where we're coming from. Negative for us means with respect to the atmosphere. So this simple cartoon here, any process which is removing CO2 from the atmosphere, that's this red arrow, may also be emitting CO2 in the atmosphere, but as long as that red arrow, either the rate or the cumulative amount of CO2 removed from the atmosphere exceeds the rate or cumulative amount of emissions into the atmosphere, that's a negative, carbon negative process, again, with respect to the atmosphere. Okay, so an example, direct air capture and storage. There's some machine, that green box on the left, which is pulling CO2 from the atmosphere, those red arrows. Running that machine may emit some CO2, that's that black arrow going up. We then compress that CO2 in order to pump it into, store it into deep saline aquifers. And that process of compression and transport may also emit some CO2. The point is, with respect to the atmosphere, the amount of CO2, that red arrow being pulled out of the atmosphere, and in this case, being put into the geosphere, exceeds the sum of those black arrows. That's a carbon negative process. So what we're talking about for carbon negative crude oil is a simple extension of that. Instead of putting the CO2 pulled from the atmosphere into a deep saline aquifer, let's put it into an oil reservoir. In so doing, we will produce oil. CO2 enhanced oil recovery is well known and long practiced process. We produce that oil and then we use it the same way we have been using oil for these many decades. So we transport it, we refine it, we combust it in various processes and engines and emit CO2. The key point here is, as long as we're pulling more CO2 out of the atmosphere and storing it in the geosphere, then the sum of all the emissions from running this entire process, that will be carbon negative. So that's what we're talking about when we say carbon negative crude oil. The crude oil itself looks like every other barrel of crude oil that's ever been produced. The carbon negativity comes from the process. It's not intrinsic to the oil itself. Okay, so we're motivated to look at this by what we're calling the exigencies of the carbon budget. So the schematic of this, an example of this is on this figure. So you see a time axis on the horizontal scale, looking at the last 30 years. The left vertical axis is carbon budget. In this case, it's the remaining amount of carbon that can be emitted into the atmosphere and still have a chance of staying below 1.5 degrees of warming. So the dark blue line is a 50% probability of staying below 1.5 degrees. And the lighter blues have got other ranges of uncertainty. So what's going on here is you see the blue line is decreasing with time. In 1990, there was 1,500 gigatons of carbon dioxide that could still be emitted and have a 50% chance of staying below 1.5 degrees. What happened in between 1990 and 2020 was that orange line, which is annual CO2 emissions, and you see it's 30 plus gigatons a year for most of that period. So for 30 years, 30 plus gigatons, yeah, that's 1,000 gigatons of CO2 were emitted. And the budget correspondingly is down around 500 gigatons now at the time of this study in 2020. Okay, here's where we come in now. So a great deal of that emissions is coming from fossil fuels and from industry. And if we simply carry on as we have been, this is a familiar story, but cast now in terms of the carbon budget, we will chew up the remaining bit of that carbon budget very quickly within a decade. So that's what's driving the issues here. That and the fact that oil is a major contributor to chewing up what's remaining in that carbon budget. So these are the average emissions for the main, for the fossil fuels and several other CO2 contributors averaged over a recent decade. And oil is running at about 12 gigatons a year. So that's what's going on now. We've got a carbon budget of not very much, and oil is chewing up a big piece of that. So the additional consideration that's now quite clear is we're going to have to do carbon dioxide removal, pull CO2 from the atmosphere and put it somewhere else in order to meet climate goals. And an illustration of this is on the left, time scale of a century now on the x-axis, and annual emissions on the y-axis. So that big green wedge is the difference between business as usual and the blue curve, which would be, in this case, limiting warming to 2 degrees. So you get that green wedge by eliminating emissions, for example, electrifying transportation, or avoiding emissions, for example, capturing CO2 being emitted from a fossil fuel combustion process and storing it. And it's a big wedge and it's a heavy lift, and not all those emissions can be readily mitigated. And that's that gray zone, which is, as you see, goes above that below 2 degree curve. So to get to a net zero emissions along the blue curve requires that lighter blue wedge down there below zero. That's negative emissions. Below zero, in this case, pulling from the atmosphere. That wedge is going to happen if we're going to meet, in this case, of 2 degrees, the net zero by 2075. But any scenario you look at, negative emissions are going to be necessary. And so a summary of that provided in the IEA's net zero emissions pathway work published last fall. They summarized, that's about 15 or 16 IPCC scenarios, the amount of carbon dioxide removal needed in 2050 in those scenarios ranges from 5 to 15 gigatons per year in 2050. That little green bar is an example of what happens as the IEA did for their NZE pathway. Try to minimize reliance on CDR. Even with attempting to minimize reliance, you still need a couple of gigatons a year of energy-related CDR in 2050. So, summary point, CDR needs to happen. Okay, what are our options? Well, there's not many. This is a recent study looking at the readiness of, in this case, 8 of the main methods for CDR that are under discussion. Top 3 rows are natural, next 3 are technological, the last 2 rows are hybrid. So one thing is there's not a lot of options here, but more importantly, I'm not going to go through this in detail, but you don't see any option which is green lit from left to right. All of these have got some reasons to be concerned whether we can build these out at scale. So we need CDR, but we don't have a lot of options for it. So that's one of our motivating factors here to discuss carbon negative crude oil. And indeed, another driver is even if we aggressively reduce oil consumption, even then it's still going to consume a lot of the carbon budget. So if we take the same net zero emissions pathway that the IEA published, I'll refer to that several times in this presentation. It's an example. Your conclusions will be similar for other pathways. Here's the area under that oil curve, basically their projection. And it's of order 200 gigatons of CO2. And you'll recall that 1.5 degree pathway example we looked at a moment ago, the current carbon budget is about 500 gigatons. So that's a lot of your available budget, even in this dramatically rapid reduction in oil consumption. Just a quick note, because we'll come back to this later. You'll note that not all of that oil is going to transportation, going to combustion. Some of it is being used as feedstock, and indeed that's part of the IEA's projection, is continued use of oil as a feedstock for materials. That will play into the possibility of also providing carbon negative crude oil for that purpose later. Okay, so the key point in all of these pathways, not just this one, but all of them, is that oil consumption is assumed to be unabatable. There is no capture and storage going with oil use. So the only options you have to mitigate oil emissions are pretty simple: use less of it. And so in this case, on the left, you see that rapid reduction in fossil fuel consumption for transportation. This is global, to be made up by renewable sources, whether in the form of electricity or in biofuels, or hydrogen, which was produced either from renewable power or from carbon-based sources, which also include CCS. The other thing you notice is that the total demand for transportation energy is projected to decrease in this pathway, which is the other way to mitigate oil use, is just not only use less, but travel less, especially in this early stages of things. You see that red wedge there, that's the oil behavioral changes for using less oil. So those are the only real options that are discussed for mitigating oil emissions. So the upshot of all these considerations is a sense of urgency, and that comes from the final point I want to emphasize here, which is the time scale. So if we look backwards in time, the y-axis there is exajoules, but this is the rate, this is the growth of consumption of fossil fuels over the last 60 years. And the point I wanted to make here is that it is very unusual for any of these energy sources to grow faster than 2 or 3% per year. Only twice in the last 60 years has sustained growth. By sustained, I mean for 15, 20, 30 years. Only twice has that rate of growth exceeded 5%. And you see it back in the 60s and 70s for oil and gas. So ramping up any energy source rapidly is difficult. So when you look at projections, and this is the same one we just looked at with NZE, these are requiring eliminating the use of fossil fuels at an annual reduction rate of 5 to 9% and sustaining that for the 15 to 30 years, which means you need to replace that with another source, which is going to have to grow even faster because the sum of these is going to be substantial. That's a big lift, right? And so we don't have a lot of time to do it. And to the extent that we don't manage to make this happen, we incur, for example, suppose the oil consumption does not go down as fast as proposed in this pathway, then that's another large chunk of the carbon budget going away. So we will need CDR regardless. We may need it even more because of the exigencies of the budget and the challenge of the time scale. That's why we're interested in carbon negative crude oil. In this case, from direct, the illustration we'll look at is from direct air capture and CO2 EOR. This can be done in the near term. It's scalable to material scale for removals. Recall, we're talking, we need to get to gigatons a year of CDR. And you can actually make oil production a net negative process if you do it right. How do you do that? That's what we'll spend a few minutes talking about now. So the schematic is like the one you've seen before, and this is the life cycle emissions of that oil, from emissions during production, then transportation, refining, distribution, et cetera, until its final combustion. The other thing that's explicit here that wasn't earlier there on the bottom right, you see the brine arrows. All oil fields produce brine along with oil. Many of them, especially the ones that are suitable for EOR, actually produce a lot more brine than they produce oil. So the key here is we're going to take some of that produced brine, and instead of adopting common practice in any oil field operation, which is to re-inject that produced brine to someplace convenient, and convenient is often the reservoir it came from, we're going to dispose of it somewhere else. And so schematic, we're showing a deep saline aquifer here. So that's the key to get the atmospheric carbon negative balance to work. That has implications for how we look at the reservoir. So we're going to talk now about how you would manage a reservoir to do this. So the carbon balance in the reservoir schematically looks like this. You've got a certain amount of carbon in that reservoir in the before the time when it's full of brine and oil. Green is oil, blue is brine. So in the course of pushing in CO2, we will produce some oil, and that's that green hashed volume. We'll also produce brine, and as mentioned, some of that we'll dispose somewhere else. So the sum of those two volumes, the produced brine volume and the oil volume that they occupied in the reservoir, that's where the CO2 that we're going to capture from the atmosphere is going to go. Okay, so essentially the management of this has to do with how much brine do you store somewhere else. And so the way to think about that is, one way to do it is look at the carbon density of the fluids in the reservoir. So what we're showing here on the y-axis, that's kilograms of carbon, just carbon atoms per cubic meter of fluid. And the fluids we're looking at are CO2 and oil. And these are the densities at reservoir conditions. So we're looking at reservoirs greater than 1 kilometer in depth, so the CO2 is supercritical. And in that state, the CO2 carbon density as a phase is a little bit short of 200 kilograms per cubic meter. The oil carbon density, and this density includes not just the oil itself, but all the associated emissions during production, refining, transportation, et cetera. So that's the all-in life cycle carbon density folded into the reservoir condition volume of the oil. Okay, so those run 600 to nearly 1,000 kilograms of carbon per cubic meter, depending on some details about the oil, the temperature, the pressure, et cetera. So the key point here is just the range. The carbon density of the oil is considerably greater than the carbon density of the CO2. So if we wish to be net negative, it doesn't suffice simply to replace the produced oil volume. You must also make some extra space because the CO2 is less efficient reservoir of carbon than the oil. So the right-hand vertical scale here is the ratio of the reservoir volume of brine that was disposed somewhere else and the reservoir volume of oil, at which we reach a carbon balance, carbon neutral. So the amount of CO2 stored in the atmosphere that was stored in the reservoir that came from the atmosphere is equal to the amount of CO2 that will go into the atmosphere as we produce, refine, combust that oil. Okay, so the values here range from 2 to 4. Okay, if we were to go to larger ratios, 5 and above, that would get us into carbon negative crude oil. Okay, so that's your point of reference here. 2 to 4 should be around carbon neutral. 5 and greater should be carbon negative crude oil. Very briefly, you'll see the oil for petrochemicals boxes down there, the hashed lines. And that's a lot smaller carbon density because the combustion is not happening. You still got emissions from production, transportation, refining, et cetera. But the point there is if we're producing oil strictly for feedstock, we have the opportunity to have a much more net negative carbon net negative crude oil. Okay, so can we do this? Can you manage a reservoir with those kinds of volumes? So first, let's look at what has happened in the past. So that graph there, the x-axis is oil removal and reservoir volumes, and the vertical axis is the net amount of brine removed. That spaghetti of colored dots and curves are field data from 35 to 40 carbon dioxide EOR projects in the Permian Basin. So what I did was draw on here the lines for 2, 3, and 4 ratio of brine to oil removal. And you'll see that had that CO2 been coming from the atmosphere, many of these projects would have been producing carbon neutral oil. Some, especially in the early stages, there on the left-hand side of this plot, would have been producing carbon negative crude oil had the CO2 come from the atmosphere. Now, they were not trying to store CO2. They were trying to produce oil and minimize their costs because they were having to pay for CO2. So even so, in running those processes, they could have been carbon neutral at least, possibly carbon negative. So what could happen? Well, here we're going to turn to a key point. Almost all the brine that was produced in those from those reservoirs got re-injected into the same reservoir. If we were to take, say, half of that brine that was produced and put it somewhere else, store it as in that schematic a couple of slides ago, what would these curves have looked like? Well, they'd look like this. So note now that the y-axis scale is twice what it was on the left-hand side. Those are much bigger numbers. Qualitatively, the curves look similar, but what you can focus on are those dashed black lines, which show a ratio of 5 reservoir volumes of brine per volume of oil up to 8. And you see that essentially all those projects, almost all of the time, would have had we run them with this disposing half of the produced brine somewhere else, would have been carbon negative crude oil producers if the CO2 came from direct air capture. So the potential for producing carbon negative crude oil is certainly supported by what happens in the field. So given that, how does this fit into the bigger picture for meeting the need for CDR? So several key points here. One is scale. Let's first look and see if this is going to be relevant at scale. So this big blue circle is the estimated potential for oil production by CO2 EOR. This came from out of the IEA a few years ago. It's in the neighborhood of 200 billion barrels. Okay, so I drew in there a little slice, which is the 1 year's oil consumption at current rates. So if we were to produce all the oil currently demanded across the globe by CO2 EOR, we could carry on doing that for decades. Okay, so there's plenty of potential there. So that's one checkbox. But the other thing to point out here is that oil being produced is, as we mentioned a while ago, contributing about 12 gigatons of CO2 to the atmosphere every year, chewing up that carbon budget. So what if we supplied part of that demand with carbon negative oil? So we pulled out that yellow wedge, and it doesn't take a whole lot of that wedge to give you material amounts of CDR. That's the point. So depending on how you run it, so we'll look at an example in a moment, if we were to produce somewhere in the range of 1 to 10 million barrels a day of carbon negative crude oil, that would enable us to also remove a gigaton a year of CO2 from the atmosphere. And that is net. That's the process we've been talking about. So you'd be using that oil, that carbon negative crude oil, in exactly the same way we've been using oil for these many decades. Okay. So the key point here is, yes, we can get the scale for CDR needed without having to build something even larger than what exists. Indeed, we could work at the margins of what exists and still have a material effect on CDR. And by the way, that is also a significant fraction of what that oil would have been contributing, chewing up from the carbon budget. It is also the case that this carbon negative crude oil can take advantage of infrastructure. And in this particular case, what's interesting, and this is from Shima Monfard, a grad student working with us. She's looking at what happens if we use the energy you're producing with the EOR. It's from using the oil directly and any associated gas. We're going to supply the power needed for direct air capture with the energy produced from the reservoir. So she's got 3 examples here which correspond to different ratios of brine removal relative to each volume of oil produced. So those green bars below the 0 line, so the y-axis is greenhouse gas emissions. Those green bars are each 1 ton of CO2 removed from the atmosphere. The bars above the 0 line are the emissions associated with the process. So the dark blue bars are all the same because it's all that 1 ton of CO2 removed by direct air capture. So those are the same for all 3 cases. How the cases differ is how much oil is produced beyond what is needed to to drive the direct air capture. So as we go from left to right, so the low carbon crude oil on the left, you wind up with net emissions of 0.22 tons. And so that's a great deal lower than it would have been had you not run the direct air capture. But if you increase that brine removal to make more space for storing CO2, you produce a smaller amount of crude oil. That red box, that red bar is the emissions from burning that oil for transportation. But in the middle case, where the ratio of brine to oil is about 4, that crude oil is essentially carbon neutral. And as you continue to increase the amount of brine removed to store more CO2 relative to the oil produced, we get to carbon negative crude oil. So the remarkable thing is twofold. A, you're working in a place where you've got somewhere to put the CO2. That's important. The wells are already there. And equally importantly, you've got a source of power to drive the direct air capture. And you can run this thing. And the key point here is indicated there in the bottom right, is over the brief description. We're not capturing any of that power generation emissions. We're simply running equipment without any capture. Okay, and you're still carbon negative. So this is one reason why this could be done in the near term and be made scalable. Also, it's clear that because of what we're producing, crude oil, which looks just like the crude oil that's been produced for decades, that is the ultimate in drop-in fuels. It goes to the same refineries and the same end users as it always has done, and to the same cut going to petrochemicals as always has done. And there's revenue associated with that. There's a global market in place, et cetera. So the infrastructure per above for actually producing it, but a great deal of infrastructure also exists for using this energy source. And that has a value above and beyond the value of removing CO2 from the atmosphere. So having these additional revenue streams is going to be important in implementing these things. So there's one other aspect of this, which I think is important to recall because the time scale for action is so short. So in addition to scalability and infrastructure and revenue, there's an aspect of hedging our bets here on net zero pathways. We will need gigaton per year CDR by 2050. And we're reviewing that here with the middle slide. No matter which pathway you look at, we're going to need it. There's 8 technologies on the table. We're proposing a 9th one, carbon negative crude oil. It's a big lift to get enough of those contributing of order gigaton a year to meet what's going to be needed under these various scenarios. So having another option is going to be important, especially one that can be implemented and scaled rapidly. The other aspect of the hedge we've talked about, it's going to be a big lift to get to net zero by 2050, no matter how you cut it. And if we, in particular, that dashed red line, if we do not eliminate oil use as fast as we need to get to 2050, regardless of your scenario, that implies continued oil use. And per above, it doesn't take long for that to chew up even more of your carbon budget than you would have already lost. So for these reasons, we think carbon negative crude oil is a potentially valuable contribution and another option to put on the table for discussing what we're going to do about carbon dioxide removal. We need things that can be done rapidly and get to scale rapidly. And we think carbon negative crude oil is such a thing. It can be done in the fields. Exactly how we wish to dial that in, as you saw with that choosing your water oil ratio, we've got some flexibility there, but it can be done based on how you want to run that reservoir. And finally, the overall key point is we can deliver more services to society in a given carbon budget if we take advantage of an option like carbon negative crude oil. So thank you very much for your attention, and I'm really looking forward to answering whatever questions may have arisen as we go through this. Thanks again.